Hello everyone, we are going to continue on the set of lectures talking about how to implement a basic kind of CPU, a central processing unit, or in short a processor, right. And as we looked at in the previous lectures, we are basically talking about some kind of a programmable processor, and what we are going to do this time around is to see how we can extend the basic functionality that we have already developed in some of the previous videos. So, the first thing that I am going to start off by talking about is something that I just kind of left aside in the discussion regarding ALU operations in previous videos. It's with regard to the idea of immediate operands. So, why do we need immediate operands and how do they get implemented in a processor? So far in the example that we looked at, right, we were essentially where we basically tried doing things like, for example, solving the equation for the discriminant of the roots of a quadratic equation, right. What we saw was that we only had like 3 parameters a, b and c, and we could perform the operations by assuming that the parameters are directly present already in some registers. Now of course we did not answer the question of how they got into the registers in the first place. But more importantly, one of the issues that we found over there was even when I wanted to just multiply something like 4 into a into c, I actually needed to perform, I needed to ensure that 4 was present somewhere in one register, and I did not really give an explanation of how 4 got into that register in the first place, right. So two things come to mind. First is when I want to multiply something by 4, it looks as though I need to do 2 steps. First is somehow get 4 into a register, which means occupying one of the registers, and the next is to actually perform the multiplication. But it seems like it should be possible to perform both of these at one shot, especially with small numbers like 4 or 2 or 1 or something like that, right. So in other words, so far all our operations were of the form add R1, R2, R3, right, where we had 3 register arguments for the operation. But there are many common scenarios where we need to use constant values. The most common one is probably, in fact the most common number that you can find in most programs is the number 0, right. In fact, there is a saying that I read somewhere once that the only numbers that are permitted to be used in computer programs are 0, 1 and infinity, and everything else should sort of be derived in other terms. But that is an extreme step, but it's a matter of fact that the 0 is probably the most common number that you are going to deal with while working with programs. Now 0 is not the only one. Very often we want to increment values, right. We write it as count plus plus in languages like C, but what we actually mean is add 1. So the question becomes, where does that 1 come from? Do I need a separating instruction just to do an increment? What if I wanted to do plus 2 instead, right? So on the other hand, I could also have something else completely different, like for example, we have already seen in embedded programming how we might need to use bit masks, where let's say I want to get the bottom 8 bits out of a 32-bit value. I would AND it with the number 0xFF and thereby extract the bottom 8 bits. So the sort of natural solution that we can think of for this would be, is there any way by which we can take immediate operands, right? Immediate arguments. Operands are essentially the R1, R2, R3, which basically mean the arguments or the values upon which the operation works. Is there a way to specify immediate operands? Immediate operands means that the operand itself is specified as part of the instruction without having to go look it up from a register. What that means is the operand would have to be embedded inside the instruction. So now that we have this as sort of a general idea on how we might approach the problem, let's look at one way by which this could actually be implemented. So what we are going to do over here is to introduce a new instruction type. We are going to call these register immediate operations. Now examples of that would be add I, RD, RS, IMM, right, and what that means is RD is equal to RS plus immediate. Now as you may recall, one of the things the previous kind of instructions would have been something of the form add RD, RS1, RS2. Now of course you could also sort of switch these around. The order of these does not really matter. It just makes sense to have RD as the first argument for various reasons that will become clear in a moment, primarily because we want to be able to represent the immediate value as well, right. But there is nothing fundamental about that. It could be any sub part of the instruction that we could use and identify as the immediate part of the argument. So, a normal instruction that we have already looked at would be of this form, where there are 3 register arguments, but here I have 2 register arguments and something else that I have labeled as IMM, immediate. The meaning of this instruction is RD is equal to RS plus immediate, and now the thing is that this immediate value is just something that is already part of this instruction. I do not need to decode it from a register, I do not need to go through the register file and extract a value. I can directly specify some number out here. Other instructions in the same vein could be subtract immediate, AND immediate, OR immediate, multiply immediate. You could have a whole bunch of different things in this way, right. So, the immediate value, in other words, is a constant that is embedded inside the instruction. Now, let us look at what that means in terms of an instruction encoding, right. We could think in terms of something like this. I have a large number of bits out here, right, and I am going to say maybe I use 1 bit to say whether this is a regular or immediate. Now, please keep in mind that this instruction encoding that I am talking about is not the final encoding that we will be working with. I am just talking about the fields that we need to specify out here and sort of trying to put them together so that we can finally then bring everything together and look at it in terms of what are the different ways in which we could encode these instructions efficiently. So, I could, given the fact that I only need to choose between register and immediate, maybe I could just decide to give 1 bit for this. Now, should that 1 bit be at the beginning of the instruction or the end of the instruction or somewhere in the middle of the instruction? That is part of the encoding process, right, and there is no fundamental reason why one or the other approach is better, although there may be some ways of arranging things that make a large class of instructions easier to decode. Now, assuming that I have these 4 instructions add, sub, mul, div, I would need 2 bits for encoding the operation, right, which means a total of 3 bits, which basically tell me whether it is that it's an ALU operation and also that it's of the immediate type or whether it's immediate or register, right. Now, of course, what if I give only 2 bits out here, it means I have only these 4 instructions that I can encode. If I wanted AND, OR, XOR, NOT, then I straight away go for another 4, which means I need at least 3 bits to encode. And let us say I also add some shift kind of instructions, that number slowly starts increasing. The point is, we need to sort of take a call on what are the kinds of instructions we want to encode and then finally decide how many bits we want over here. And now comes the operands, right. So, the first operand that I have, I am going to use it to encode RD, and in this case I will use 3 bits. Basically, I am assuming that I have 8 registers, right, and then as you can see from the previous case over here, I still have at least 1 source register. I do not have instructions over here to just add 2 fixed quantities, and there is a reason for that, because the assumption is that adding 2 fixed quantities is something that could actually be done at so called compile time, right. You do not actually need to write a program in order to add them, right. So, if I have 2 known quantities, I should probably just perform the operation and just store the final value that I need over there, right. There may be scenarios where you don't, where you actually explicitly load constant values and multiply them, but still it is not a common enough operation to have a separate kind of instruction for it. We assume that one of the operands is always in a register and the second one is an immediate operand. So, RD, and I also have RS, which is again 3 bits because I have the same set of 8 registers. And now finally I have, let us say, RS2, which could be 3 bits, right, or I might choose to repurpose the same set of bits and say that I am now going to store an immediate value out here. But if I have only 3 bits for an immediate value, it sort of severely restricts the range of values that I can have. It pretty much only goes from -4 to +3. I mean, I just have 8 values that I can store. So, perhaps I add on another 2 bits and basically make this a 5-bit immediate value, right, which basically means that I can now represent values in the range -16 to +15. Right. Now, is that good enough? Maybe, maybe not. If you wanted to add more, then you would basically need to extend the number of bits for the immediate operand, which basically means that it would also affect the total number of bits in the instruction size itself, right. So, this is basically the instruction length that you have available to you. Now, once you have a certain instruction length, right? What we are trying to do over here is to sort of see how we divide it up in a way that essentially allows us to partition across and figure out how the different parts of the instruction need to be allocated. So, as I said, there are many common use cases for immediate operands. One is just initializing to 0, right? And since, as I mentioned, just empirically people have observed that 0 is probably the most common operand, the immediate operand that is used. Many CPUs actually do something else. They say that rather than just sort of trying to use 0 as an immediate operand, why not just fix one of the registers R0 to the value 0, right? And this is not necessary, this is not fundamentally necessary, right, because there are plenty of processors and instruction sets that do not follow this, but especially the type of RISC or the reduced instruction set compute architectures like MIPS or ARM tend to have things like this. So, RISC-V for example also follows this R0 equal to 0 approach. Now, basically what that means is R0 is frozen in hardware, it cannot be changed, right. Even if you try assigning something to R0, it is not going to sort of crash the CPU or anything, but it will just ignore the write and it will not change the value in R0. Now, why do they do that? Primarily because most of these architectures also tend to have quite a large number of registers, which means that using one of them as a fixed 0 is not a big cost, and the benefits in terms of how easy it is to sort of initialize values and do various other things in terms of adding and also of simplifying certain kinds of instruction implementations outweigh the cost that is associated with losing one register. Now, there are other use cases, incrementing by 1, where we would basically have an add immediate instruction that looked something like this, add I R1 R1 1, right. If we did not have this, we would need some other register to store the value 1, so this is good to have. Similarly, let us say I wanted to mask out an operation, I have a variable x, I wanted to get these 4 bits, that is to the bits 7 to 4 out of the whatever operand, whatever value is there in x, I can AND it by having an AND operation like this. Now, here is the problem, we just discussed a case where the immediate operand was only 5 bits in size, but clearly this is an 8-bit immediate operand. So, it is not going to work with only a 5-bit immediate operand. If you had only a 5-bit immediate operand, you might be able to do 0x0f, but not 0xf0, right. This is a trade-off. If you wanted to still figure out how to get 4 bits, you might have to do a shift first and then figure out how to AND out and get the bits that you want. Now, the question becomes, how do we implement something like this, right? And it's actually, if you look at it, it's not all that complicated. All that happens is our ALU gets a little bit more complicated. We already had the operation, which is the AND or add, subtract and so on, but now there is an additional input called use immediate, right. And what we have is there is a RS value, that is the first source register. There is also an RT value, we could call this RS1 value and RS2 value, or RS value and RT value, it does not really matter. We also have an immediate input, right. So, this immediate input over here is what is decoded from the instruction, and of course finally we have an output result. So, the changes that we have is, one is that we have one input which is just a boolean value, yes or no, saying whether to use the immediate value, and of course you also have the actual immediate value itself. Now, keep in mind that our actual register values and the final result are 32 bits in this case. Well, they were 8 bits for our example, but this is what it would look like if you were working with 32-bit data, right. Now, with this 32-bit data that we have over here, one of the things that we would recognize is a 5-bit immediate value seems problematic, right, because how do I make it a 32-bit value? Well, the answer is fairly simple, we basically sign extend the immediate value to 32 bits. So, we only have a number in the range minus 16 to plus 15, and this is basically sign extended out to 32 bits, right. So, if it was a negative number, I would basically add 27 ones in front of the MSB. If it was a positive number that starts with a 0, I would add 27 zeros in front, right, and that is easy enough to implement in Verilog. So, now I have this temporary intermediate variable called extended immediate, and now I need to select which is the second operand that needs to go into the actual ALU operation. So, operand B is going to be, if the use immediate value, the Boolean signal is true, I will use extended immediate, else I will use the RT value. And once I have done that, the rest of my ALU looks exactly the same as before. All that it says is do RS value plus operand B minus operand B ampersand, or whatever are the operations that I need to perform out here. Just use operand B instead of the RS2 or RT value. Now what about large constants? As we saw, we can use only a 5-bit immediate operand with our current encoding. That's not always true, right? I mean, we might choose an encoding where we have larger immediate operands, but at some point we are always going to hit a limit. The point is you can get around that. Let's say that you wanted to load a 16-bit value into a register, right? Or not quite a 16-bit value, but at least a 10-bit value, something like this, right? 0x3e8, right, into R1. The way that we could do it would be add immediate R1 R015. Now notice what we have done here. We use the fact that R0 is always 0, so that I can just add 15 into R0, put the result in R1, and it gets the value 15. If I did not have this, I would need a kind of a move instruction, right? And in fact, many processors have some kind of a move or move immediate, certain kinds of operations of this sort. Strictly speaking, this is not necessary provided that you have an instruction of this sort, right? And RISC-V, for example, takes this approach, where they say that they don't have a move instruction, they will get the same behavior by using something like this. So in this example, here we found that in order to load the value 15 into R1, I could basically give R0 as one of the operands. This essentially using add to get the equivalent functionality of move, right, where we don't need a separate move instruction, is something that would not be possible if we explicitly needed to use a separate instruction in order to load a register with 0. Then we would pretty much have to make sure that we have a move instruction separately. It's a trade-off. These are engineering choices. There's no hard and fast rule that says one or the other is the correct way of doing things. And in fact, if you go through history, you will find that there are processors that have pretty much used every single different alternative that you could have out here, right? So this is one convention. It's not necessarily the only way of designing things. Turns out to be quite useful in practice and is used especially in processors like the RISC-V architecture. So to summarize the need for immediate operands, they basically allow you to use constants without having to load them from external storage, right? We don't yet know what external storage is, but we don't need to even worry about, how do we get data into a register. We can basically have constants directly as part of the instruction. However, because they are part of the instruction, they have to be by definition smaller than the size of the instruction itself, because part of the instruction is used for encoding the instruction and only whatever remains can be used for the immediate operand. Using this convention of R0 having the value 0 provides a constant 0 source, which can be quite powerful in many use cases. Now, where do we use these kind of immediate operands? Multiple scenarios. Initialization is probably the most common one. Increments, decrements, bit manipulation, all of those come to mind as simple and obvious cases. Essentially, it enables you to have more efficient code by reducing the use of registers, right? Especially when you want to do something like 1 or 2 or some small immediate operands, you can directly have them as part of your instruction and not have to explicitly load them into a register and then try to do something with it.